This is an old radio from the 1940s. As you can see, it's huge and very heavy, but it looks great, so I thought I'd use it as the basis for a project. Now, although it's old, it's not particularly rare or valuable, and it wasn't working. I don't know why, and even if I could repair and restore it to be a functioning radio again, I didn't really want the risk of putting 230 volts across these 80-year-old glass vacuum tubes. So I replaced the original circuitry and put an ESP32 inside while keeping the exterior and the original controls, including these dials, the speaker and grille cover and the tuning wheel. And this is the result. So if I turn the radio on, you'll see it lights up, and well, initially we've got quite a lot of static, so let me just try and adjust that tuning dial until we can hear that a bit more clearly. So we've got a number of different radio stations. Each one is broadcasting on a different frequency and they're all playing a unique playlist. So let me just tune to a radio station I like. That's pretty cool, we've got some cool trumpet jazz. That's quite loud, so I'm just going to turn the volume dial down a bit so you can still hear me. So pretty much this is behaving as you'd expect a regular radio to do so, but I didn't just want to stop there. Besides playing music, I wanted this to be an interactive prop, so as well as having different stations you can listen to, I wanted to be able to interrupt those broadcasts with breaking news reports.
We interrupt this broadcast to bring you a breaking news announcement from Playful Technology. Regular scheduled programming will now resume.
Now, the playlist of music tracks for each station and those announcements are saved on an SD card, so you can store hours of music and hundreds of messages, and you can trigger those externally from a sensor or a remote button input like this, or from control software in an escape room. So let me show you how I made this, starting with the rewiring of the electronic controls. So for the on-off switch, that's just a simple switch that makes or breaks a connection. You can read the result using any digital GPIO pin. There's also a multi-way select switch, which was used to swap the radio between shortwave, medium wave and long wave. I'm not actually making use of that for now, but you can see how it works. In each position, a different pair of pins are connected together, and you can read those on a GPIO pin. The volume dial is a potentiometer, so you can connect ground to one side and a positive voltage to the other. And as you turn the dial, the value at the output pin in the middle will vary between those two extremes. So I've connected ground on one side and 3.3 volts to the other end terminal, and then I read the value from the output pin using one of the ESP32 analog inputs. Now, the tuning wheel is a little bit more complicated as it has both mechanical and electronic elements. The tuning knob is connected via a pulley system to this large wheel, which has a piece of string wrapped around it. Now, as the wheel rotates, it pulls the string and the indicator up and down to show the frequency which the radio is tuned to. But it also turns the leaves on this variable capacitor. As you increase the overlap between the metal leaves, the capacitance increases, and in the original design, that's what changes the frequency of the radio broadcast received. Now, I originally wanted to measure that capacitance change directly, similar to the way that I read the volume dial, but it's a little bit harder to do that. The common method to measure capacitance is to apply a current through a resistor and then remove that charge and time how long it takes for the capacitor to discharge again. I did try that, but the results I got were very inaccurate. We're only talking about very small changes of capacitance here, measured in picofarads, which combined with timing inaccuracies, all the noise from the environment, meant that I just couldn't get a clean reading. So instead I decided to cheat a little bit and rely on every escape room's favourite sensor, which is a magnetic hall sensor, which I placed just behind the end of the capacitor here. And then I glued two small magnets onto the back leaf of the tuning capacitor. Now, the magnets are reverse polarity, so one has its north pole facing this way, and then the other one, which I placed right at the other end of the leaf, has its south pole facing this way. And now as I rotate the knob, the hall sensor here detects a change in magnetic field strength from extreme positive at one end to extreme negative at the other. And we can define the frequency of the radio stations that we want players to be able to listen to as lying on any point in that spectrum between them. I'm using an SD card reader to access the audio files. The playlist for each radio station is saved as an hour-long WAV file that just runs on a continuous loop. And I'm playing the audio output through an I2S amplifier, which is then wired up to the original speaker. Now, to trigger the breaking news announcement, I'm using this small RF switch and taking the result through an optocoupler module to the ESP32. So that means I can press the button on an RF fob like this and read the output just using a regular digital read. So this is a great way of adding a remote trigger to any Arduino or ESP32 project. It's really simple and cheap to use. Now for the lights on the front, I'm using these PL9823 programmable LEDs. I didn't really need to use RGB LEDs, but I do have a little bit of animation because I make them fade up and down with a slight orange glow to make them more closely resemble the effect from the original incandescent light bulbs that would have been used. The entire radio is powered from the 5-volt power supply coming from a single USB line, and that provides plenty enough power for it to be surprisingly loud. And this wiring diagram illustrates how I've got all those components connected. It feels like this project is a great showcase for the ESP32 as it demonstrates quite a few different sorts of interfaces. So starting with the on-off switch, that's a simple digital input which is connected to GPIO pin 4, and we'll set that pin to use the input pull-up mode in the code, so it will read high by default and then low when the knob is turned and the switch is connected through to ground. Here's the RF switch which I use to trigger the breaking news interruption. Now this must be powered with a voltage between 5 and 24 volts on the red and black wires, and it outputs that same voltage on the blue and white wires when turned on or off via the remote fob. Now the maximum voltage you can apply at an ESP32 input pin is 3.3 volts, so instead of wiring the switch directly, I'm taking that output wire to an optocoupler instead. Now, when you press the button to activate the switch, the 5-volt output here lights up an LED inside the coupler, which is detected by a phototransistor, and that allows 3.3 volts to come from this line here and be applied to the GPIO pin. So it's a safe way of reading higher voltage inputs that you could normally not read directly on a GPIO pin. Then we've got the LED lights over here that light up the glass behind the tuner, and they are a digital output. Now I'm using GPIO pin 13 to carry the data signal into the first LED, and then you connect the data out from each LED to the data in of the next in the series. I'm using PL9823 LEDs which come in 5mm form factor, but you could also use WS2812B or any other similar programmable 5-volt LEDs that all use the same protocol. Then we've got two analog inputs, so we've got the volume dial and also the Hall sensor which we're using to detect the magnets on the tuning dial. Now these both require 3.3 volts, ground, and they give a output that is somewhere in a range between those two values, which we then read on one of the analog input pins. So I'm using GPIO pins 34 for the volume and 35 for the Hall sensor. Now the SD card here uses an SPI interface, so that connects to the default ESP32 MISO, MOSI and clock lines, which are pins 18, 19 and 23, as well as to a select line on GPIO pin 5. Now one thing that's worth noting is that although the SD card reader and that SPI interface all run at 3.3 volt logic, the SD card module I'm using, and most that I've seen, require a 5-volt power supply, and that's just dropped down to 3.3 volts on the board via a regulator. And finally, we've got a Max 98357 amplifier which uses the I2S audio interface. So this requires power and ground lines and 3 lines for data and clock, which I've connected to GPIO pins 22, 25 and 26. Now it also has a gain setting which I've connected through to ground, and a shutdown pin which I've connected to 3.3 volts to ensure the amplifier is always enabled. And this is the code that's running on the ESP32. An awful lot of this reuses common patterns that I've used in my previous projects here, so hopefully won't be too much of a surprise to you, but I'll step through any particularly interesting or unusual bits. So we start at the top with some includes. These are required to access the SD card where I'm saving the audio files. And these two includes are part of the Arduino audio tools library, which I also used in my last project about tracing a glyph. And this is doing basically all of the heavy work when it comes to loading and processing the audio files and sending them to the output as well. It's a fantastic library. And I'm also using another great workhorse library. This is the Fast LED library, which I'm using for the LED control. I'm not really using much functionality of it here, but it is also a great library. I define 3 states that the radio can be in. Very simply, it can be off or on, or we can be broadcasting the breaking news. And the behavior of the radio is going to differ later on depending on which state it's currently in. Then we get a section of constants. These are basically where I define the pins which are mapped to each of the components, matching the wiring diagram which I just showed you. And we also define the different radio stations that we want to be able to tune into. So I've got 3 audio files saved on my SD card, very simply called 001, 002 and 003. And these are the frequencies, as it were, that we want the player to be able to tune into to listen to them. You can define as many as you want. What these correspond to is the value returned from the analog reading of the hall sensor, where I had those 2 magnets on either side of the variable capacitor that was twisted around when you turn the tuning dial. This value here corresponds to the reading that you'll get from that. So don't think of it as an actual frequency as such, but it's what's acting as a proxy for the frequency that you're listening to. But you can make as many of these as you want. You just need to make sure that they are sufficiently distinct frequencies away from each other that you'll be able to tune into one of them without getting cross interference from another one. These files themselves, these are just hour-long uncompressed WAV files, 44 kilohertz 16-bit format, which I've saved on the SD card, and they're just going to loop over and over whenever the tuner is set to within range of that frequency. We get some global variables, so I'm using the I2S stream from the Arduino audio tools library, and as well as playing the WAV files that correspond to those radio stations. As the tuning frequency becomes further and further away from here, what I'm going to do is I'm going to mix in white noise. That's how I'm generating the effect that the radio is slightly detuned. And the Arduino audio tools library also comes with its own built-in white noise generator. So I'm creating one of those. The value here is the maximum amplitude of the noise that will be created. And I found that if you let that be full volume, it's actually really quite obnoxiously loud. So I've set that to a limit of 600 there. And I'm also going to create an encoded audio stream. That's what's going to load the WAV files from the radio stations above here. And I'm going to create a mixer object and a volume stream, which I'm going to put into the audio pipeline connecting these 2 objects here. So I've got a white noise input and I've also got a wave input here. I'm going to send them into a mixer, and basically what I'm going to do is, as you are closer to being in tune, as it were, to a radio station, the relative volume of the station is going to go up and the relative volume of the white noise is going to go down. And then as you move further and further away, we're going to increase the volume of the white noise and decrease the volume of the WAV file until you get so far away from the radio station that you're currently listening to that it gets unloaded completely. And as you approach the next radio station, what I'm going to do is swap in the next audio file instead. And I always do that at a point when it is completely white noise. So in the background, basically, you never notice this being changed, I'm just going to reuse the same wave decoder to load whichever one of these you're closest to and then play that in the background and gradually fade it up or down using the mixer. The volume stream is actually the global volume stream of the radio altogether, so that's what's going to be set when you turn the volume dial up and down. We define the audio file we're going to load in the SD card, the array of LEDs we're going to control. These values here, these basically just keep track of what the last known station you're listening to, what the last volume, the tuner setting and things like that, so that we can detect when any of these values have changed. So this is basically used as a simple debounce, and I'm also going to use that a bit later on to output to the serial monitor some useful debug information just so we can keep track of what the current state of the radio is in. So we initialize all those, we initialize it off, and we specify the format in which our audio files are saved in. And this also has to match the format in which the white noise is going to be generated in. So we'll generate the white noise to match the wave audio format, and then we can blend between them without having to do any more conversion. That's going to make less work for the ESP32 to have to do if it doesn't have to do all that conversion and blending. Incidentally, that's also the same reason why I'm using WAV files rather than MP3 files in this case. I've got an 8GB SD card in the reader anyway, so I've got plenty of space, and a WAV file can be streamed more easily than an MP3 file, which is compressed, so it has to be sent through a codec first and decoded. So that's why I'm using WAV files. We get to the setup function. This is fairly typical, so we initialize a serial monitor. I'm just using that for debugging. We initialize the LEDs, and we're going to make them yellow. We initialize the on-off pin as an input pull-up, as I mentioned, so that when it is switched, it is connected to ground. We read that down. And we initialize the optocoupler that is connected to that RF switch. We keep track of the last RF value. We set that in the setup function here so that we know what state this was in. The RF switch I've got is a toggle switch, basically. Every time I press that key fob in my hand, what it does is simply toggles on and off. And we don't necessarily know at the point we're running the setup function which state it's currently in. So unlike the on-off switch, which we can actually say, is it on or off, this we don't know. All we can tell is has it changed since the last reading. So that's why I set the value of last RF input in the setup function here. We load the first audio file from the SD card just so that we've got something to play ready, so it sort of queues up the first value even if we end up changing that later. We initialize the I2S interface based on the pins which I showed in the wiring diagram. We start the white noise, we also start the mixer, and we begin the volume stream. So all these functions here, these are all from the Arduino Audio Tools library, and it's about setting up this audio pipeline where we can load files from audio files, we can blend in noise. If, for example, you had a microphone, you could also have a microphone input here as well, and perhaps instead of playing a pre-saved wave file announcement, you might want to speak that out loud. You could do that instead. So you'd simply define a different input here, and you'd add that into the mixer, and you could change the code so that your mixer blended in your microphone input rather than an MP3 or a WAV file or a white noise instead. This is a simple helper function here, which is just going to provide a little bit of smoothing. So because we are reading some analog inputs, the volume dial and the tuning dial, and they can be a little bit jittery, and we don't want the code to kind of be jumping the volume around all the time. We want to smooth that volume out and smooth the frequency reading out. So this is a, it's not actually a true Kalman filter, but it's kind of a simplified version of one that runs very quickly, and you can just provide it an input and it will give you a smooth result out. That's all that's doing. So don't worry too much about the maths behind that. And then we get into the main program loop. So this runs over and over for as long as the code is being executed. And what happens in this loop, largely depends on what state the radio is in. So these three states up here of off or on or braking determine what's going to happen in the loop function. But first of all, we're going to read whether the remote fob has been pressed by reading that digital pin there. And if it has, which means that if the value we've just read is different from the last value, then we are going to immediately change to the breaking news state. When we do that, we're going to override whichever audio file was previously playing with the interrupt.wav file instead, which is saved on the SD card. And that is the spoken announcement. And to create that audio for the announcement, I used a text-to-speech engine called F5. Now the way this works is that you provide an audio sample of a voice that you want to clone. Here I've got a small snippet of a genuine BBC News radio broadcast from 1940.
Most of this bulletin is concerned with the war in Norway and on the North Sea, and of developments in the United States and Scandinavia.
And you also provide a transcript of the words that are spoken in that audio sample, which enables the engine to learn the accent and the pronunciation that you want to emulate. And then in this box here, you can type any text at all that you want to be spoken. It will be said in the style of the provided audio sample. And then if I click the run button, it will generate a WAV file output containing that message.
This is an example message which will be said in the style of the provided audio sample.
Now that's quite low quality, but actually that works really well for this example of being a 1940s radio broadcast. Obviously if I provided a different vocal input here, the quality here can be much improved. Now, I only demonstrated a single announcement in this video, so every time I press the remote fob, the same message is going to be played back. But you could record as many of these different audio samples as you like and have them triggered at random or based on specific inputs. If you were using this radio as a clue delivery system in an escape room, you could record different audio hints that were triggered in response to players' actions, or after a certain amount of time had elapsed in the room. Now, WAV files have a 44-byte header at the beginning of them, so we just want to ignore that and get onto the raw audio data, so we seek to the 44th byte. And then what we do is we set the mixer weight of the 0 channel to 100 and the mixer weight of the first channel to 0. So what this means here is that when the breaking news interruption is broadcast, effectively we want it to be perfectly in tune. Remember where I described at the top of the code I was going to blend white noise with the audio file of the station that was currently playing up here based on how well tuned it was. But when we get that breaking news announcement, we basically want to pretend that that message is going to be broadcast absolutely crisply and perfectly, however close to a radio station we were. So what we do is we set the weight of the white noise that's being fed into our mixer on channel 1, we set that to 0, and we set the weight of the interruption here to 100. So that's the equivalent of fading out all of the white noise and making this a nice crisp broadcast there. So that's what happens if we've pressed the remote fob button. Otherwise, we enter this state here. So if we are playing breaking news already, we call the copier.copy function. Now, what this does is this basically is a way of buffering the audio data that needs to be sent to the I2S amplifier. So this is a function that's part of the Arduino Audio Tools library. You plug that pipeline into it that had the white noise and the WAV file and the noise volume and all the rest of it. And at the end, if there is data to send to the amplifier, that's what this copier.copy function does. Now, when our breaking news file here has ended, however, when we get to the end of this file, then copier.copy is going to return 0. This function normally returns the number of bytes that have been sent to the audio output. So when that returns 0, which is why we've got the little exclamation mark here, we know that we were in the breaking news state, but the breaking news announcement that we were playing up here has finished. So in that case, what we want to do is we want to return back to the last station we were listening to. That's what this line here does. Again, we skip the header at the beginning of the WAV file and we just return back to a default state of being on again. Now, if the radio was off, well, when it's off, the only thing we want the radio to do is wait until it's turned on, very simply. So in the off state, this is nice and simple. All we do is do a digital read of the on-off pin. And if that is connected through to ground, then we know the radio's been turned on. And this is where we just do our little bit of animation just to make the LEDs light up with a nice orange glow. So we loop over them and gradually fade them up to a hue of 60. So that's just what gives that effect of like an old-fashioned bulb being turned on. It's purely aesthetic, this. But most importantly is that if we were off and the on-off switch is pressed, then we are now in an on state. And then when we are in the state that the radio is on, well, this is where the majority of the actual code execution happens, okay? So the things that we do when we're in the on state, well, the first thing we want to do is check whether we've been turned off again. So this is the exact inverse complement to the section of code we just had up here. Instead of listening to be turned on, we check whether it's been turned off, and if it is, we fade the LEDs out again and set the state to off. Otherwise, we're still on, so what we want to do is we want to check what volume we are at. So we take an analog reading of the pin that is connected to the output of the volume potentiometer. We feed it into that Kalman smoothing function above that I mentioned. That's just going to get rid of any jitters where the volume would spike up and down. We don't want to have that. We want to have a nice smooth volume. If the volume is changed, I've got some commented outlines here that you can put to the serial print if you want, just so that you know what the current volume is. Otherwise, we're going to set the volume stream based on the smoothed volume. Volume stream takes a float value between 0 and 1, but vol, which we're getting from an analog read, takes a value between 0 and 4095. So we just divide that to get that into the correct ratio to pass to the Arduino audio stream's vol stream. So that's our first control, our first dial that we want to read when the radio's on. The next one we want to read is the tuner value. Now this is a little bit more complicated. So what happens here, first of all, we simply take an analog reading of the hall sensor pin. And again, here I've got a slightly different smoothing method. I found that the sort of noise I was returning from the potentiometer, the volume pin, and the noise I was returning from the hall sensor pin were different. So I've applied slightly different smoothing functions to them. And then what we need to do is based on this value of where the tuner, where the hall sensor is reading, we need to work out what is the radio station we are closest to listening to, and that's what this block of code does here. So we assume first of all that the index of the radio station is -1, so that's basically saying an invalid station. We haven't found one at all yet, and that station of -1 is 65,535 away. These are both kind of invalid values, as it were. And what we're going to do is step through this loop and update those with a better candidate for a radio station that we can listen to instead. So we loop over all the stations one at a time, and we calculate the absolute distance between the tuner position that we've measured from the hall sensor after it's been smoothed, the difference between that and each of the stations that we defined at the top here. So we're taking an absolute difference. If the tuner is set to 2020 or if it's set to 1980, the absolute difference from this station here is going to be 20 either way. So we're 20 away from that one, but we are significantly further away from either of these stations. So this is going to be our closest station. And we loop over all the stations, and for each one we calculate that distance. And if that distance is closer than the distance of any of the other stations that we've found so far, we'll replace our best candidate with that new station. So we loop over all of them, and again, this is actually a very, very common pattern for finding a value from an array. You loop over the entire array, you keep track of what your best candidate is so far on some metric that you want to decide, and then you just pick that one at the end. So we get to the end of the array, we have found our closest station, and we have found the index of it in the stations array here. Now, if the station that we are currently closest to, if the frequency of that station is different from the station that we're currently listening to, what that means is that we have moved the tuner a sufficient distance away. If you're just at that point where you could just be tuning into it or not, I didn't want the audio file for that station to constantly be loaded and unloaded all the time. So I've added a little bit of an extra condition here to make sure that you are sufficiently close to the new station. So basically we're saying that the station that we're closest to now is not the one that the radio is currently playing, and we are also sufficiently close to the new station to make it worth changing it, basically. Then what we say is we are retuning the radio. We will close the audio file associated with the radio station that's currently playing, and we will open the file of the new closest radio station instead. Once again, we seek past the wave header at the beginning of the file, and then we start playing it. This line here is the line where we determine how much of the radio broadcast we're going to blend in compared to how much white noise we're going to blend in. So depending on the sensitivity, the Hall sensor you're using, depending on the range of values it's returning, and depending on, frankly, how accurate you want users to have to be, you can try changing these values here so that there's a greater or a lesser kind of fall off either side of the optimal value. Essentially, we don't want people to have to tune into exactly 2000 because you're not going to get an exact value from an analog reading of a Hall sensor. You're going to have some degree of approximation and noise in that reading. And the line I was just looking at basically is a tolerance of how far either side of these values you can be and still pick them up as a radio station. So you might want to experiment with those values to see what works out for you. That's what I've got. And I've called that signal strength because when we go to the mixer that's going to be responsible for mixing together the radio station and the white noise, the radio station is going to have signal strength applied to it, whereas the white noise is going to have the inverse, 1 minus signal strength. So there's always going to be some blend between them, with the exception of the interrupt, the radio interruption announcement, which was always going to be set to 100% accuracy. So that's what made it crisp and in tune all the time. Once again, we call copier.copy. So this is the Arduino Audio Tools method that actually sends the I2S data to the amplifier, and whatever audio file we've loaded up here, so whatever our closest index that we're listening to is, and however we've assigned the volume between that and the white noise in the mixer, this is going to send that calculated value out to the amplifier to play on the speaker. And right at the bottom here, this is just a section for debugging. If it has been more than a second since the last time we output some serial information, I'm just going to dump a load of information. So the current state of the radio, the volume, the frequency, and the station we are currently listening to. And you might find that useful when you're first developing this to make sure everything is working as correctly. And for when you're trying to tune values like that. Oh, I said tune, didn't really mean that pun. But these values here, when you're trying to set these appropriately to get the behaviour you want. So that brings me to the end of this video. I hope you found it useful and that it's given you some ideas and knowledge you can use in creating a similar prop to this yourself. Now it's worth mentioning that had this been a functioning radio receiver, I probably would have taken a completely different approach, leaving it intact and instead using the ESP32 to broadcast a genuine shortwave radio signal, basically a very low power radio transmitter, which you could then tune the radio to normally on whatever frequency the ESP32 was broadcasting on. Now that would have meant I wouldn't have had to rewire any of the electronics, and I could have left the original radio completely as is. But it does generate some other problems. If this is a functioning radio, then yes, it will pick up my intended broadcast containing my carefully curated playlist of thematically appropriate music, but it will also pick up every other real radio station in range. So you'll get the news, the weather, the latest Ed Sheeran song, some phone-in quiz, which is kind of going to break the 1940s ambience that I was trying to achieve. Now, the method I followed here is more destructive and it's more effort, but by faking the radio stations that are received, it does give you complete control. And even if you don't want to create a radio, hopefully this project might have demonstrated some other techniques, how you can wire to other old devices, how you can use an RF fob to remotely trigger your controllers, or how to use I2S audio, which you can use in lots of different ways. Now, as always, I'll be uploading the wiring diagram and the Arduino code to download on my Patreon account, and I'll put a link to that in the description below. That's also where you can find the resources to accompany all of the projects I've ever published in this channel. And it helps me to continue making more tutorials like this in the future. I also have a Discord server where you can get assistance with creating these kind of escape room projects and other great playful technology that's being made by amazing folks all over the world. Other than that, I just want to say thank you all very much for watching, and I look forward to seeing you again next time. Okay, cheers, bye.